in the cloud. Okay, for example, Amazon Web Service, they have cloud computers and so on. Then a lot of these problems that we may not be able to solve in the past, say 20, 30 years ago, okay, when we have 3G, 4G. Now, maybe going forward 4G to 5G, 6G, we could utilize cloud computing to solve this problem. Surely we can leverage the large percentage of the computing infrastructure, right, to search for valid coloring, right, on this graph. Okay, and maybe if I'm the designer of the 6G network, I would then ask Google to help me, right, to solve this graph coloring problem. But at the same time, right, if Google can solve it, so Google is the prover, right, and he wants to prove to me that he can solve this problem. Well, Google is not going to give me the solution, right, if I'm not able to pay Google, right? Because Google has utilized its computing power, its data structure, to come up with the solution. So then, therefore, there's in real life, actually, just also in real life, there's a matter of trust between two parties, right? The verifier and the prover. Prover has something that the verifier wants, and how would the verifier knows that the prover has solved that problem? Okay, so the verifier wants to know with zero knowledge, meaning that the verifier, that means I'm the network designer, I want to know that Google can solve it, right? Google, without releasing that solution to me, so the verifier, me, I do not have knowledge of the solution, the computational solution, but I want to know that Google can do it. Because maybe then I can, if Google cannot do it, right, then I can maybe ask another cloud provider to solve it and so on. So what Google would do then, right, for zero knowledge proof is then to say that, hey, let's play a game, sort of. What this zero knowledge proof is saying that you could sort of verify the solution, right, periodically, right? On each iteration, maybe you just inspect, say, a small subset of the solution. For example, just now it was a big graph, right, remember? And Google has colored all possible nodes in the graph such that it satisfies the three color constraint. Okay, and so now what Google does is that it covers all the nodes, right, in black, so I could not see the color, and I could then say, hey, I want this edge, to inspect the edge and look at the two nodes connecting the edge. Okay, and suppose the two nodes are of different color, then I'm somewhat convinced that, hey, Google has the solution. But at that moment, Google doesn't show me the incomplete graph yet. So I could repeat this this experiment. But what Google does is then to reshuffle the colors, right? You could do a mapping to reshuffle the colors, right? And then recolor. And then again, repeat this test to say that, hey, choose any edge at random, and then ask me to say, hey, look at the two nodes connecting that edge. And if they are of different color, then I am going to be more confident that, hey, Google has a solution. So this can be repeated many times on the same graph, right? So then when I have done this multiple times, then, you know, the verifier myself will be very certain that, you know, Google has the solution, despite the fact that Google at that moment hasn't revealed its complete solution to me. Okay, so that in a nutshell is an example of using this 5G, 6G frequency assignment to demonstrate to you the power of zero knowledge. Okay, so I think in the following slides, I'm going to show you, you know, how information theoretic tools, right, can come in useful, right, in such a setting. Okay, so yeah, Nikki, thank you so much. I'm going to say next later, and then you just next. Okay, thank you again. So indeed, if I look at the historical developments of proof, okay, as I said, zero knowledge proof started in 1980s. Okay, but way before that, we all have indulged in proof, right? We like beautiful proof. Okay? And indeed, at the turn of this century, around the last century, right, 1900s, David Hilbert, who is a very authoritative mathematician in his days in Paris, right, had a conference and he laid down 23 problems that he said are deserved to be solved. Okay, and people all know these 23 problems and they try to crack it. And in fact, some of those problems comes with prizes, money. Okay, so if you're able to solve it, you become a millionaire overnight. Okay. But turns out that there is one problem, the 24th problem, that Hubert, he did not announce it at that conference, and it was later on discovered by historians. Okay, same also around 1980s. So therefore, it is called the 24th problem. Okay, what is the 24th problem? And here's what David says. Okay, David Hubert. He says, well, we do not have computers yet. Remember, it's at the turn of the last century, 1900s. But he says that indeed this is a real problem. We want to automate proof. That would be great. Okay, if we could use some machine to automate proof. Okay, maybe using axiomatic or any logical approach. But he says this: it would be aesthetic, right, or very pleasing to the eyes, to the human eyes, that if we could develop proof that are simple, right? So there could be criteria to quantify simplicity of proof. Okay, for example, just now I just mentioned zero knowledge proof, in which you have still this notion of proof, but it is much more complex. Okay, so if we could develop a theory of the method of proof in mathematics in general, right, and we could sort of explore all possible proof. But David believed that there is one and only one simplest proof, okay, for any of these problems, and preferably we should go for the simplest one. Okay, so this is a very crystal clear kind of a definition of the simplest proof, right? So it's like a quest for the simplest proof in any problems or systems that human wants to develop. Okay, so next, please. So here I'm going to, in the next few slides, going to sort of introduce to you one possible scenario and how to achieve the simplest proof. To prove what? As we are in the communication community, and as you know by now, cryptography and communications, they all have roots as well in information theory. So it would be very nice to solve some of these problems in information share with you a few of these information theoretical sort of entropy, mutual information, and so on. These are so-called information theoretic functions of random variables. Okay, and use a lot in cryptography. And so we want, say, suppose I have again these two parties. Remember, a prover and a verifier. And now the verifier says that, hey, I have this information theoretic inequality. For example, entropy of a random variable greater or equals to 0, right? So it's a simple result. Okay, the entropy of a random variable h and then x, for example, is it greater or equals to 0? So that's the statement. And I'm just wondering, is this true for any random variable x? Okay, but what you see is that it is also an inequality. Okay, so the prover then has the task of saying that, I know the proof, and to that question, right, is it true or false? The prover says, I can answer yes or no. Okay, if he says yes, then he has the proof. Okay, but on the other hand, if the verifier, has an information inequality that is false, okay, and he wants to ask the prover to prove, then the prover must not be able to fool the verifier and say that, hey, there's a proof when there isn't. Okay, so this is a very, very, very subtle point, a very interesting point about trust, for example. then in this case, if indeed the information inequality, for example, h of x less or equals to 0, suppose the verifier say, hey, verify that this is true. H of x less or equals to 0. We all know, right, from our information theory class that this cannot be true. But suppose, as a toy example, the verifier presented this, and the prover says, hey, this is false. And here's the counter example. And so even in this situation, the prover perhaps wants to come up with the smallest, the simplest counter example and be able to show that statement is false. Okay. So here I'm going to show you how we could use optimization theory to automate the search for the simplest proof or even counter example, right, in the context of information theory. Okay. And this work was published 2 years ago, and we also presented this at the ISTT tutorial this year. Okay. Next, please. Yeah. So just now I gave you a very simple example, h of x greater or less or equals to 0. But in principle, right, there could be very complex information inequality. For example, like this one, it consists of a lot of random variables like x, y, z. So you can see up here, there's 3 random variables. And so the information inequality being presented is to say, prove that this is true or false. Okay. And here you could see that I offer two proof. Okay. One is saying that the information inequality can be rewritten, right, into proof number 1. And so by inspection, I look at it, right, and you invite anyone to look at it and say, hey, look at this thing. You see that it consists of the sum of mutual information. And we all know, right, say mutual information is not negative. Using that fact, then you can easily convince yourself that, hey, this is true. But I could have a slightly more complicated proof, a longer one, that nevertheless still prove that statement. For example, proof number 2. Then you may say, hey, wonder aloud and say, well, yes, formally that is true, but it's hardly readable by a human, right? Maybe by machine, yes, but by human, they will have a hard time to be convinced. Okay. So indeed, it is very interesting to ask, can we find the simplest, in other words, the proof that may involve the fewest number of these information theoretic measures. For example, when I say information theoretic measure, it means the entropy or mutual information quantities and so on. Okay. Next, please. So indeed, again, back to this proof of simplicity. So what is the criteria of simplicity? Albert Einstein has also said, right, also at the turn of the last century, saying that everything should be made as simple but not simpler, right? And next, please. And next, please. Yeah. So and another mathematician says, well, the elegance of a proof, right, lies in the fact that it also offers, value to the statement itself. For example, the elegance of a theorem, right, or an engineering system is perhaps directly proportional to the number of, ideas that one can see in that systems or in that theorem, and inversely proportional to the effort it takes for a human to appreciate that. Okay, so I guess this applies both to math and also to man-made engineering systems. Okay, so indeed, if we can quantify the simplicity of a proof by, say, as few things as possible. Here, for example, few things, it could mean it means the number of information theoretic measures to quantify the inequality. Yeah, next, please. So here's the idea. And it's also new. How can we use optimization tools, right, to solve that problem? That problem is a problem of formal, you could think of it as formal reasoning, or automated reasoning. Okay. And turns out that a tool called convex optimization has matured in the last 40, 50 years. Okay. So turns out that this convex optimization tools can be used to enable what I have just introduced to you just now, right? The search for simpler proof to information inequality. Next, please. So here's the question, right? So how to find the shortest proof? So then, as I just mentioned, we are going to use the convex optimization tools. We are going to leverage heavily on two concepts in convex optimization, such as duality. So later on, you will appreciate that Lagrange duality, right, which is a very important part of this convex optimization, will be the key, right, to give a proof, right, the fewest proof to an information inequality. And we show you how it can be constructed using cloud computing. Okay, yeah. Next, please. Next, please. Yeah. Right. So here's the sort of like think of it in this way. In the 2000, right? There is, for example, a new way being developed to look at information theoretic inequality using linear program. Okay. For example, on the left, that's what you see, the primer. We call this a primer linear program. Okay. For example, you want to minimize linear inequality, and here the H, it really sort of represents the information theoretic measure, right? The joint entropy, depending on how many random variables you have. Okay, so H is a non-negative vector, okay? Element-wise non-negative. Okay? So here, the B is some coefficients, right? It could be integer, it could be real. So B transpose H therefore allows you to describe your information inequality. Okay? And now subject to some constraints. There's a D, there's a E. Now, do not worry about the E first. The D really, it is, think of this as some given matrix that consists of all possible elemental inequalities that describe, the constraints that your random variables can lie, right? For example, they must be non-negative, H, X non-negative, for example, and also the conditional entropy being non-negative and so on, and mutual information being non-negative. So these are all described in D. Okay. So around 20 years ago, Raymond Yang came out with this linear program, right, to describe information inequality. And what is interesting is that he only studied the primer, but not the dual. And we all know linear programs, it has primer and dual. Dual is also a linear program. And dual linear program holds the key, right? To say, suppose I have an information inequality, B transpose H. I want to ask if this is non-negative or not, right? So Raymond Yang, he sort of say, I can solve this linear program using interior point solver and just inspect the objective function, right? So if I solve this as a linear program and I look at the optimal value of the solution, of the optimal value after solving this program, if it's non-negative, then I say, oh, B transpose H is always non-negative. But suppose I solve this linear program, primer linear program, I look at the optimal value, it is negative. Then I say that the statement B transpose H being non-negative is false. I could make that claim. So in other words, by solving a linear program, I could verify whether that information inequality is true or not, right? It's true or false, okay? So that is a Boolean outcome, but I still do not know the proof. If it's true, I do not know the proof. I only know it is true, okay? So as I mentioned, the dual linear program will actually then hold the key to tell you what's the proof, okay? Next, please. Yeah, so here, this is what I just mentioned, right? So by just inspecting the optimal value P star, right, of solving this linear program, okay? If it's non-negative, then I say it's true, and if it's negative, then I say it certainly is false. If it's a Shannon type inequality. But what is very tricky is that there's a class of so-called non-Shannon type inequality A famous one is also discovered by Raymond Young and Zhang in 1998. So in other words, solving this linear program is not sufficient in general to claim any information inequality. Okay, it only works for Shannon type information inequality. Okay. Next, please. Yeah. So here's the short proof. Okay, to showing why the Lagrange dual holds the key. Okay, and it is very simple. It comes from the Karush-Kuhn-Tucker condition, the KKT. So as we all know, right, convex optimization is very nice because there's zero duality gap. Primer meets dual, right? And at the point where they meet, this is what we have the Karush-Kuhn-Tucker condition, the KKT, that describe the point where they meet. Okay, the optimal primer and optimal dual meet together in a set of system of equation. Okay? And by solving this system of equations, and that's given over here, you see that we could then derive, for example, on the left, B transpose H. That is the inequality what we want to prove. And that is equal to this quantity on the right. Okay? And notice that this quantity on the right, the Y star is the Lagrange dual, optimal Lagrange dual, and the mu star is the optimal Lagrange dual corresponding to the constraints in the primer problem. Okay, and from KKT we know that this Y star is non-negative. Okay, so if I look at this every term on the right hand side, you see Y is non-negative and D times H is non-negative by definition in the primer constraint, and also in the primer constraint there's a equality, zero equality constraint, right? E times H equals 0. So this whole thing will be 0 regardless of mu. And then that boils down to the whole thing being non-negative. Okay? So in other words, if I could find the right Lagrange dual solution, the optimal one in fact, right? And form these systems here, I could then prove that that inequality being given to me, B transpose H, is always non-negative. Okay. Now, at this moment, I like to sort of give you a geometrical meaning to Y transpose D times H. So remember that D is a matrix, right? So time. Okay. So Y transpose times D times H, okay, is as if I am choosing certain rows in D. Which row to choose? For example, is where you see, as I just mentioned, Y element wise is not negative. There will be a lot of zeros, but some are non-zero, and those that are non-zero will be positive. If I could choose those rows as few as possible, I'm trying to recombine those rows together to prove my given information inequality B transpose H. That is the physical meaning to this mathematical description. Okay, Y transpose times D times H. Okay, so I hope this is clear, right? So next, please. Yeah. So next, please. So here is the idea: how to search for the Y. Still remember that's our Lagrange dual. That is the sparsest. So now here you see that I've linked simplest with sparsest. S-P-A-R-E-S-T. That means the sparsest vector. The vector with the most number of zeros. That's what I want, because then I could have fewer rows in the D being involved. And if you recall the earlier slides, that will allow me to have fewer information theoretic measure that I could then inspect easily to be in all non-zero. Okay. So next, please. Yeah. So here's another optimization framework now. For example, now you see right at the top, I want to minimize the vector Y, and there's a mu as well, which is all of the Lagrange dual vector. And this is a L0 norm minimization. Some of you may be familiar from the compressed sensing days. So I'm trying to find the sparsest vector and then try to solve it. And we know it's hard to solve. So we use a convex relaxation method to turn an L0 norm minimization to an L1 norm minimization, which is convex optimization. Next, please. Next, please. Yeah. So in other words, by solving the dual, I could, and in fact, I should say, to be more precise, by solving that convex relaxation, minimize the L1, I could then get, hopefully sparsest Lagrange dual. And if I check that they are all non-negative, well, then I can make a claim saying that, yes, I have a proof, right? The information inequality you have given me is true. If, I do not have the solution, for example, the interior point or simplex algorithm tell me that, hey, there's no solution to the K key, then I could immediately go back to the verifier and say that, hey, look here, the information inequality you have given me is either false or this verifier. Okay. So next, please. Next, please. Yeah. So the next few slides I will skip because we are trying to look at scale. A bottleneck in the thing that I just mentioned lies in the fact that the matrix D, right, which is the elemental information inequality, the constraint, more and more number of random variables. In the case, right, in machine learning examples in 5G, 6G, we have more random variables. So the more variables you have, the bigger the matrix D will be, right? It grows exponentially large. So then we want to have scalable, low complexity method to solve the convex relaxation problem still. So here we have, look at so-called ADMM, alternating direction method of multipliers. And these were very cool optimization techniques developed, say, around 10 years ago by Stephen Boyd and many others. So the idea is that to use first order method instead of interior point method efficiently and also in a distributed manner. Okay, so next, please. Yeah, that's the algorithm. So I will not go into the details. All right, next, please. Next, please. Yeah, so what I've just described is that we have used ADMM to solve this gigantic convex relaxation. And it will be very important to extend this sort of infrastructure, right, to make it available to many more people. For example, if I have that thing being solved on my local computer, it only helps me. But imagine if I could use the same thing to help many more people to verify their information inequality by just using one single D matrix, no matter how big, right, in the cloud, that is going to be very beneficial, right? I just have one single huge D matrix, one single convex relaxation. So every time I would get different B transpose H from different people who wants to prove their information inequality, they could use my system. And I could then say that, hey, it's true, and here's the proof. Hey, that one is false, and here's the smallest counterexample. And for example, somebody give me a non-Shannon type information inequality. We couldn't prove it 2 years ago, but now this we could, using the same framework to say that, hey, that information, that non-Shannon type information inequality using our similar systems, you could prove that it is true or false. Okay. So very naturally to the notion of cloud computing, like what I just described before. If I want to have an engineering system 5G, 6G, I could utilize the cloud to help me to get a proof. Next, please. So in the next few slides, I will quickly walk through, right, some of these cloud computing developments in the last few years. Okay. Next, please. Yeah, I'm going to skip some of these slides. Next, please. Yeah. Next, please. A quick sort of overview of some of these developments. So as I mentioned, 20 years ago, after Raymond Young came out with the linear program framework, he also came out with the software in MATLAB, right? That can only verify, but not prove, right, any information inequality. And also around the same time, 2008, around 10 years later, there was this XITIP. In fact, people like David Chee at Stanford now and so on, they contributed to these ideas of making a more robust XITIP. And only later on, around 2014, we discovered this idea of using the Lagrange dual to develop proof and counter examples. And over the last, say, 5 to 6 years, we saw similar ideas being developed. For example, Shishma, who is a cryptography expert, he also has this thing called the minimal information theoretic inequality prover, right? Mini ETIP, right? You can find online. So all this, what happened was that this Shishma work was to turn the MATLAB work into a C program so that it can run very fast, but it doesn't still provide proof. Okay. So later on, we, upon our work 2014, we developed this into a cloud computing service, and then we released it to the public. And also, indeed, there were other cloud computing services. So think of this as a software as a service, right? Or platform as a service, approval as a service kind of facility, right? To prove information inequality. Okay. So next, please. Yeah. For example, ITIP, Raymond Yang. So you can see that you can go to download the MATLAB, but then it only serves you, right, on your local computer. Next, please. And it only verifies, not proof. Okay. Next, please. Next, please. Yeah. So that's the framework for XITIP. And again, that's just locally, right? But it's faster than the MATLAB. It's built on C++. Next, please. And that's the old XITIP, online online XITIP, right? Which they developed on the cloud. Again, this web interface makes it convenient. Anyone can use it now without installing MATLAB. And now what happened here is that this software can only verify still, just like ITIP running on the cloud. Okay. Next, please. Yeah. So this is the mini ITIP, as I mentioned, written in C, right? Which also runs very fast, but only could be used locally, right? Instead of on the cloud. Okay. Next, please. So here's the AITIP that we developed. We call this the Automated Information Theoretic Inequality Prover. It will then offer the same service that you saw just now, but in addition, it provides proof, right? So if your information inequality is true, it gives you the proof. And if it's not true, it will tell you, give you hints to say, construct a counterexample to disprove that by solving the convex relaxation problem that you just saw. Okay. Next, please. Let me walk you through some example, okay, using this AITIP. Next, please. For example, the first one is the so-called data processing inequality. Again, a 101 information inequality we see in class. For example, I want to prove this inequality, between 3 random variables, and these 3 random variables, they are constrained, right? Subject to a constraint that X, Y, Z, they form a Markov chain. So that's our constraint. And I want to say, is this information inequality true or not? The mutual information between, the 2 ends, right, is going to be smaller than, a subset. Okay. So using this, I could derive the proof. Next, please. And here's the proof given by our systems, right? For example, you see that this thing at the bottom, it says the objective, right? Which is just now you saw the mutual information involving the 3 random variables. So that's the one over here. The one it says the objective can be written as you can see, this summation, sum with plus, sum with minus of joint entropy. They can be written equal, right? As adding 2 rows of the D matrix. So you see that 2 rows has been selected. And since the D times H is not negative, we know each one of these is not negative, okay? And then you can then combine them to show that they are not negative. Okay? And therefore, the information inequality to be proved is true indeed. It's not always non-negative. Okay. Next, please. Yeah, and the most well-recognized result in cryptography. So now back to our zero-knowledge proof, which is its application in cryptography and also blockchain and so on. Right, has its roots in the information theoretic of perfect secrecy, right? A theorem derived by Shannon in 1949. Okay, so here's the result that Shannon developed in 1949. He says that constraining your system, right, to make it perfect secrecy is that, well, you see the first inequality, the first constraint is that, well, if I have the so encrypted message is a random variable X, okay? Then, sorry, if you can go to the previous slide again. No, go up. It's fine to go up some more. Go up. Go up some more. One more. Yeah, one more up. Yeah, thank you. Yeah, thank you. Yeah, so let me sort of describe to you. For example, now given this encrypted message and the message, I know nothing more. For example, the mutual information is 0, meaning that they are the same. Okay, and suppose I have the key, which is R, and the encrypted message X. We all know that you have the key, you can open the door. So that tells you the message. So with the key and the encrypted message, that's good enough. So that's why this second constraint is here. And these two constraints together describe perfect secrecy. And so Shannon said, is this information inequality true or not? That means that the entropy of the key, R, is always greater than the entropy of the message being encrypted. Sorry. So he proved in 1949 this is a true information inequality. So now, using our systems, we could derive the proof. Next, please.
Dr. Tan,
yes.
One more minute, yeah?
Yeah, sorry. Sorry, next, please. Yeah. Yeah. So here's the slide that shows it's okay. You see that HR minus HU, you want to show that it's non-negative. It can be written as the conic combination of the rows of the D. Still remember I said select those Ds and then weigh them with the Lagrange tool. Combine them together, that's the proof. Okay. So here's the proof in just combining 4 rows, and I get a proof that there's a correct information inequality and verify what Shannon has claimed. Okay. So next, please. I'm just going to skip the disproving part. Okay. Next, please. For example, if your information inequality is false, then I can disprove it. Okay. Next, please. Next, please. Yeah. So let me lay down a few open issues and conclude this talk. So indeed, I think what is interesting is that we are at the AI era, right? So automated reasoning, trying to prove theorems and how to interact between 2 parties, so-called multi-party computation, a verifier, approval, and many more people, right? So trying to solve a problem together. I think there is one interesting thing that is trust in the problem that we are facing. How do we engineer trust? So what is also interesting is that absence of evidence is not evidence of absence. Okay, so I thought that is very interesting because it says that if I cannot prove something, it does not mean that that problem cannot be solved. And so that really spurred us, our community, to keep on looking at many different ways to solve our problems. Maybe building a secure, better 5G, 6G, a better and secure Web3 blockchain services, and so on. Okay, but coming back here, I think there's a lot of computational challenge. For example, solving the convex relaxation involving large constraint sets? And how do we incorporate the fact that, try to bridge the gap between formal logic and automated reasoning by optimization? As you can see, optimization requires you to solve things numerically. So you may encounter things like a numerical approximation or floating point errors and so on. So next, please. Yeah. So, and I think this community is still growing. So, trying to combine AI with information theory and AI and communication theory, and so I do really look forward to more interaction with all the participants. Feel free to write me emails, and hopefully there's a chance for me to meet in person to really explore problems of this nature, right? Distributed computation for AI in communications, in information theory, and so on. So with that, let me thank you very much. Thank you.
Dr. Tan, we'll wait for if they have any question from the floor.
Sure. No problem.
Or online. All right, Dr. Tan is waiting for the question from the floor on online. I have a question.
Yeah.
The one that you have developed with your team, I think it's a very innovative algorithm. So in this case, if we have the XITIP to verify, so what's the next application in the 5 and 6G for this algorithm?
That's a very good question. In fact, I know that you see that interesting thing is that in the talk that I just introduced, I hope that there was some takeaway. For example, how we might see 5G, 6G as graph coloring, and then there's a need to know how to color the graph. I need a proof to build this thing, right? And maybe there are some things that I cannot build. For example, with the spectrums, maybe in the future, there will be more constraints on some spectrum that we can use. For example, the aircraft is using some spectrum that is being released by the FCC for use by, on Earth base. So how to avoid interactions, the so-called interference and so on. So therefore, I think what we are looking at, back to the question 5G, 6G, is that we are going to the IoT age, where more things interact now, and they may interfere, and there's also the problem of secrecy, right? Or so-called cybersecurity coming into all this picture. So how can we make things more secure in future wireless systems? I think that's interesting. Maybe Shannon has shown us the way with his perfect secrecy theorem in 1949, and now 2022, we have come a long way. But what we know that in the future, systems will be bigger, more in other words, involving more random variables. Just now, the 1949 example I show you was 3 random variables, right? The key, the message to be encrypted, and the encrypted message, right? R, M, and the U. 3 random variables, and Shannon proved that in 1949. But now here, the problems, for example, in machine learning, in network coding problems, they have many more random variables because each node is like a random variable. So your network has more nodes, more variable, high engineer system. This kind of interesting. Yeah.
All right. Thank you, Dr. Tan. I think there's no question from the floor and online. I'll pass it to the MC of the floor.